Hi and welcome to our skill workshop of AMIRIS. AMIRIS is the open agent-based market model for the investigation of renewable and integrated energy systems. And yeah, first thing, a warm welcome from us. In today, there is myself presenting and also my two colleagues, Felix Nitsch and Johannes Kochems, who will be in here. If there is any technical issues or stuff like that, they will help us and support us in any case you have experiencing any technical difficulties in running the model. Okay, so first, what's the motivation of modeling the electricity market with AMIRIS? So first, the transformation towards a renewable dominated energy system, of course, comes with rising shares of fluctuating renewable energies. And these need to be aligned with the demand side as well. So the alignment of supply and demand is rather challenging and difficult. And also for investments on the renewable side and also for flexibilities, there is or there might be rather high uncertainties if these investments refinance. So on the other hand, the energy system is a complex system, and the market actors need to behave under uncertainty, and they have interdependencies between the actors. And these interdependencies may cause emerging and nonlinear effects on the market itself. So we try to understand these market effects and the market effects in general of renewable energy integration. And we therefore need to consider the actors' behavior, their uncertainties, and also market distortions, for example, caused by the regulatory framework. And in the end, we want to develop policy instruments to incite a system-friendly behavior, both for investment and operational decisions. Okay. So what is AMIRIS in general? AMIRIS is an agent-based electricity market model, and it simulates the trading and operation of power generation plants and flexibility options, and also to some extent the demand side. And it models the business-oriented behavior of the agents under uncertainty on a time resolution of usually 1 hour, but can be even higher time resolution, and with the spatial resolution of market zones. And in order to run AMIRIS, what you need is you need input data on the existing power plants. You need feed-in potential of the renewable energy sources, a demand series, for example, demand time series. You also need efficiencies of power plants, their availabilities, and prices of fuels and CO2. When you put that into AMIRIS, you will get on the output side, you will get electricity prices, the dispatch of the power plants, their full load hours maybe, their market values, and from the system side also costs for operating the system and for giving support or paying support instruments, and also CO2 emissions. Right, that is in general the input-output side of AMIRIS. The graph you see on the right, and we'll have a more detailed look on that and what is actually happening in there, but you will see this graph more often today, so I will not explain the details for now. Okay, so, but before we dive into the details of AMIRIS, we would like to ask you, who are you? What is your background? So we will just paste in a short link to our Slido page, if not happened yet. Yes, I understood that already. Okay, thank you. So we ask you to jump onto the Slido page, and I will open the poll and to show what is your skill level with the energy systems model in general. So what do you know about energy systems? What is your expertise level on that? So please feel free to enter. Results coming up. Okay, not bad. Not bad at all. Okay. Any more votes coming up? No. Okay. So, and the next question is, are you familiar with agent-based modeling? So what is your familiarity with that type of modeling? Okay. Rather not so. Some say yes, they know it, and others say never use it before, obviously, or not so really familiar with that. Okay, you can see the results, right, on your screen. Is that correct? Just
At least I can see them.
yeah, okay.
I'm not sure about the others.
Cool. Okay. So we have some experts and some newbies, but we'll have the level of the workshop rather introductional. So I hope we can have we can catch everyone. If there are any issues, please don't hesitate to ask questions directly on Slido. We'll have an eye on that. And also, if there's something really unclear, just interrupt me, raise your hand. I mean, we're not that a big group, so you can really interrupt me just and ask questions if there is anything really with an issue or missing from your side. Okay, perfect. So let's dive deeper. Thank you for your information on who you are. Now, I promise you, you will see the agents plots more often today, and let's have a deeper look at what is actually happening with these agents. So as AMIRIS is an agent-based model, everything is centered around the agents and their interactions. So there are different types of agents in AMIRIS that do their stuff, and we classify them in this graph by color. So for example, there are markets, they determine prices. Yeah, we have CO2 markets, the fuels market, and the day-ahead market for electricity. We have plant operators that control power plants. They control their operation and know about the costs for operating these power plants. We have conventional and renewable power plants in here. Then we have traders. Traders try to market the power plants at the market. So they try to find marketing strategies, both for the conventional and the renewable side. We have traders, and also for the supply side, the demand is also a trader operating on the market. Then we have flexibility providers like storage operators. They try to optimize their dispatch and try to earn money from this optimization, basically. And you can also think of neighboring markets as kind of flexibility interacting with an AMIRIS. And then we have information providers, or basically the information provider forecaster, which creates forecasts of the electricity price, which is required for the storage operators, for example, to make their optimization in the first place. And also policy providers, in this case, the support policy. And the support policy offers policy instruments supporting mainly renewable power plants. Okay, so that is the structure of the agents. But from this structure, you can see that, I mean, that is only the agents itself, but we are missing the interactions. So from these interactions, they make the whole simulation. So the question is, how do these agents interact? And
I'm sorry, there's one question.
Yes.
About what we mean by market agents. Do we mean market operators, since the market itself is just a coordination mechanism?
Yeah, so we're not modeling like the energy exchange company, for example. So, but it's an agent in that sense that it's an instance that fulfills a certain task. So in this case, to determine the prices. Whoever posted the question, can you please indicate if that is a sufficient answer or if you require more details? Yes, no, I can't see it. Okay. So if there is further questions, please just ask again. And okay. So what we've seen here is just plain agents, but what we really need to know about is how these agents interact. The whole of the simulation is coming from how these agents interact actually. And we'll have one like spotlight of interactions here, and that is the renewable kind of chain of interactions. So what we see here are the renewable agents. So the power plant operators, the renewable power plant operators, they calculate marginal costs for operating power plants and availabilities of the power plant, and they will then, once they are assigned dispatch, they will operate that and dispatch the power plants. On the other hand, there is the renewable traders. Renewable traders create bids based on marginal cost. And they interact with the support policy in order to get money for supporting the renewable power plants. And the support policy calculates support tariffs and provides that support to the traders, which is then forwarded to the power plant operators. And the day-ahead market agent, which is simply collecting the bids from the supply and demand side and clears the market. That's and provides this information to its clients, namely the traders again. Okay, so that was on a very high level of abstraction. Let's dive deeper how this is actually done. So we start with the renewable power plant operator. The input parameters of that renewable power plant operator is what kind of energy carrier it is using. In this case, it's a wind onshore, or we can think of it as a wind turbine in this case, with an installed power of 1,000 megawatts and operational costs of 10 euros per megawatt hour. And we also get a yield profile, so that will tell us at which point in time we can produce how much, or we can offer how much electricity from power generation. Okay, and based on that, we will calculate a power potential at any given time t. We will calculate a power potential, for example, 497 megawatt that we can produce. And with this power potential, we associate the marginal costs, in this case for operating our power plants, which is simply the operational costs, here the variable operational costs. And this marginal information is then transferred to the trader, which will create, which we see in the next slide, which will create a bid from it. But we will wait for the trader to do that, and the trader will come back to us and assign us power production. In this case, everything is assigned, and we will run the power plant as planned with 497 megawatts in the given time. And that is the dispatch of the power plant. And we're done. And we log this, and then we're done with this agent in this time step. The renewable trader on the other hand, receives the marginal cost from the plant operator. So it receives the information we just created in a plant operator, and then asks for support instruments for that specific wind turbine, which could be, for example, a market premium of 45 euros per megawatt hour that we actually feed in. And since we need to feed in order to get the market premium, we have an incentive to bid with negative prices. In this case, we bid with minus 35 euros per megawatt hour. And this bid is then forwarded to the energy exchange, and at there we wait for market clearing. Once the energy exchange clears the market, it returns to us how much energy we actually awarded or which power we actually awarded, and we will forward this information to the plant operator and ask for dispatch. Okay. Now, I mentioned the support policy. The support policy needs to know which kind of clients are there, which kind of energy carriers are there, which policy instruments exist. That is the input of the support policy. And it will track the power prices at the energy exchange, as well as the feed-in potential for each energy carrier from the plant operators. And based on this information, it calculates variable tariffs for each of the different energy carriers and feed-in instruments. And these can be asked by the traders and used in order to derive their bids. So these support information and payments are then forwarded to the trader, to the traders. Okay, the demand side is not so complicated. On the demand side, we simply have a value of lost load, which is in our case here 3,000. That's 4,000 in the meantime. So value of lost load has increased to 4,000 euros per megawatt hour. And a demand series, which is simply a time series, telling us at which time we need how much energy. And from this information, we create a bid. For example, we need TD amount of only like 1 gigawatt and assign this value of lost load as our maximum price and forward it to the energy exchange. And that's basically it, because yeah, we do not track the demand side too closely. So that's basically done for the demand side. And finally, at the energy exchange, all this information is brought together. That means first we receive the bids from the supply traders and the demand traders and stack them up. And then we perform a market clearing, which will lead to the well-known merit order and awards for different power plants, which are offered prices below the clearing price, or below or at the clearing price. And these awards are then forwarded to the traders and to do their stuff with that, as we've seen before. So that is basically the whole interaction chain for the renewables, but we have different interaction chains as well for the conventional traders. So you see it indicated in this graph. There is also an interaction chain starting from which power plant exists on the conventional plant holders, the conventional plant operators. They also need to interact with fuels and need to know about fuels and CO2 prices and stuff like that. So yeah, we won't go into details about that, but if you need further information on that, we are happy to tell you everything that is needed. Yeah. Okay, that concludes the theory part. Not so fast. One more important thing. So now we've talked about AMIRIS, but AMIRIS is not a standalone modeling but AMIRIS is based on a driver framework. And this framework is called FAME, the Open Framework for Distributed Agent-Based Modeling of Energy Systems. And we're using this to run AMIRIS and to operate it and also to configure AMIRIS. So we want to show you one time how this actually works in the background. So from the application of AMIRIS, we start, and from the Java code, we derive a schema that defines what AMIRIS actually can do, which agents exist, what they need, what they can do, and stuff like that. And these informations are stored in a schema file, which is used by FAME.io, first important component of FAME, to read and validate configuration files and time series files and join them together into a single binary input file. This binary input file is compatible. You can create it on any computer and transfer it to any another computer, and then feed it into FAME core that can be run on small computer like desktop PCs as yours, or maybe also like a high performance computers. And therefore it is parallelization capable. And once your computation is done, you get output files also in binary format from FAME core that are then extracted into CSV result files, again by FAME.io. Okay, if you ever need more details about how that works, we have two JOS publications for FAME core and FAME.io put down there. You can check the links later. But for today, don't worry, it's way easier because we prepared a small Python package. It's called AMIRIS.py, and it will deal with all of these things for you. So you do not need to do individual steps. It's a single command that will get your AMIRIS to run, configure, execute, and decompress the result files for you. Okay. Are there any questions up so far? That would be a good point to ask questions. Anything on Slido?
No, there's nothing new on
No?
Slido.
Okay. Okay. Too easy for you, huh? Okay, I see. So in this case, I ask you to get your PC ready because now we're doing it. Every one of you can do it on his or her own. So let's get on the hands-on part and do the setup. Okay. So AMIRIS has two major requirements. One is Java and the other is Python. So what you need to do is, if you haven't done it before as instructed, I would ask you to do like on your console, do like Java -- version on your console. You can see my console, right?
Christoph, before we start, there's a question about market premium and how it
Yes.
is determined by policy providers. I'm not sure if you want to answer it right now or afterwards.
No, we can have a short question. I just need to hop over to the.
It's in the Zoom chat, actually.
It's in Zoom. How is market premium determined by the policy providers? Thank you. So the market premium is basically determined by, depends on the actual type of premium you're using. So if you have like a fixed market premium, then it's configured. So you can determine the market premium before the simulation and need to determine yourself. Or if you have a variable market premium in our case, or for example, contracts for difference scheme, then you would need to specify the policy assumption of the levelized cost of electricity for that agent. So, or for that kind of renewable power generation device. So for example, if you have a wind turbine set and that wind turbine, you assume it has a levelized cost of electricity of this and that, then you would use that as a reference value, and from that calculate the actual market value of that, and the difference would be compensated by the policy provider. A, is that correct, Johannes? B, is that sufficient, Sahid?
Yeah, that's correct. So we need some exogenous inputs to parameterize, but also some calculations are under the hood, as you said correctly, for the variable market premium.
Okay, Said is also satisfied. Thank you. Perfect. So if Java minus, you can see the console, right, as well?
Yes,
Yeah.
we do.
That's right.
Yes, yeah, okay, just to make sure. So if the console puts out anything like anything on OpenJDK and it should be version 11 or higher, then you're fine and good to go. If not, there is a link in the chat maybe that will highlight you how to download Java OpenJDK, which is cost-free and easy to install usually. So usually, you could install 11 or 17, which are the recommended versions or long-term support versions. And the other command, of course, what we needed is, as I mentioned, Python. So the same goes for Python. Python minus version. And it should output something like 3.8 or higher in your case. So yeah. If you have that both, then you're ready to go, good to go. That's all we need for today. Anyone experiencing trouble, please contact Felix or Johannes in the chat. They can help you if you don't have that. Okay. So at least one person needs to download that. Okay, so we're proceeding slowly. So if you're having Python, by the way, yeah, if you don't have Python, we recommend like Conda or MambaForge for Windows users. That's the easiest. Yeah. Okay. Now, next steps. Next steps in order to actually get AMIRIS set up is we need to create an environment. So I'm using Mamba for that. You can also use Conda for that, or I don't know about Linux experts. They might use more like venv maybe, but in this example, I'm using Mamba to create this environment. One hint on the website, AMIRIS env was spelled with a minor, not a capital A, but a small a. So I think you can make this transfer. Python equals 3.8. 3.9 would also work. 3.10 might work. And I need to install as well. Just going with you step by step. So we need to wait a second to install. Ah, Felix is getting ahead of me. Yeah, if you already have the environment, activate it. Exactly. And install AMIRIS Pi, which is the next two steps going down. Okay. Is this taking so long? It is. I shouldn't have deleted that just for showing. Ah. Did I do anything wrong?
I don't think so. It just takes, it's a lot of dependencies, so probably takes a while.
Time for coffee? Yeah, I fear for Python interference. I'm sorry. I really had bad experience with interference of Python. I won't install it in the base. But thanks for the suggestion. It never took so long. In all my life, I never waited so long for Python environment to actually. Never mind. It just got stuck. Okay, coming through. Yes, great. I'm sorry. And we'll activate this environment using the command outlined there. So simply conda activate the new environment. And here we are. Okay. Perfect. Now let's do pip install AMIRIS Pi. AMIRIS Pi is the Python tool I mentioned, which will solve most of your troubles with handling AMIRIS, make it very convenient to use. So simply pip install AMIRIS Pi. And
while it's installing, Christoph, we have another
yes.
question on Slido.
Yes, please. Just ask it.
Yeah, Anonymous asks that in some quarters, nuclear, both conventional and small modular, is quite favored. Have you looked at mixed renewables nuclear interactions with nuclear under a low capacity factor?
That sounds more like have you looked at? How can I can't open this question. I'm sorry, I can't read it. Damn it.
Maybe I can try to jump in. So most of the studies we've done so far, most of the applications focus on the Federal Republic of Germany. And therefore, most of the time we stick to the German political targets, and we have just experienced a nuclear phase out, and also the discussions about small and modular reactors are not so very intensely debated within Germany. So for our analysis, it has not really been at the focus.
Thank you, Johannes. Okay, finally, my AMIRIS Pi has also installed. And now, since AMIRIS will download stuff like that, and I don't want to clutter it up on my C drive, I will just make a small folder, AMIRIS, and move into that folder to have everything together in a small place that I can later delete. Maybe you want to delete this as well later. I don't know. We'll see. And therefore, now we are in the folder AMIRIS, and let's do the last command, which is simply AMIRIS install. And this will download AMIRIS, the executable, and a sample in configuration files that we will use. And we're done already. So has downloaded, and quick ls command yields the status of that, we'll have the examples folder, we have the AMIRIS core jar file, and a setup YAML file. Has everybody achieved that as far as me finally did achieve that? Or are there
Maybe in the
questions?
meantime, we have another question. It
Yes.
was about whether we include capacity markets in our model.
No. Not directly. Okay. Any indications that you succeeded would be cool. Or that you need more time. Otherwise, I would progress. Okay. Works for me. Perfect. Okay. We have at least 3 positive responses. Okay. So we'll slowly advance. Okay. When you look at the folder that you created, or maybe not create, but at least at the folder that I created, you will see basically you will see 3 components. One is the examples folder, which contains configuration files. We'll have a look in that in a second. We'll have the AMIRIS executable, the latest one, automatically downloaded from our latest pipeline. And we have the famous setup YAML, which I will not go into and which you ignore for today and will probably ignore for a long time if you don't know what you're doing. So we're ignoring it, but it's required. Don't delete it. Okay. Then when we go into the examples folder, in the examples folder, you will find basically three subfolders. These are example scenario compilations from our side. And in this, these 3 examples were a very simple one, which we'll use now, and 2 more sophisticated, dated to historical countries or reproducing historical results, kind of, which will be Austria and Germany in the year 2019. And we will use the German one just later. And when you open the simple file or simple folder in there, you will also recognize that in the simple folder, you can ignore the license file. It's simply that is everything is licensed. But the important file for us is the scenario YAML. This is the central file that binds all of the other data or things in this folder together. And this will be used for our next step. Okay, because the next step is to run AMIRIS actually. And for this, you can open up the console again. And in the console, simply print or enter AMIRIS run. This is an incomplete command. And it will highlight that you need to specify 2 important things. One is jar file and the other one is the scenario file. So basically, we require these 2 arguments, minus jar, or in short -j, and minus scenario, or in short -s. And we need to specify the AMIRIS executable for the jar file and the scenario file that I just highlighted in the examples folder down below as the scenario file that we want to execute. So the complete command looks more like this. AMIRIS run -j to indicate the AMIRIS executable. Simply type in and hit the tab will autocomplete this lengthy name of a file, and then a space -s to indicate the scenario file. And we go down to the simple scenario YAML. That means we go to examples, simple scenario YAML. There we go. And when you have it, simply press enter and it's running. So basically what you now see is the following. First, you see that AMIRIS is trying to start up. So the script is running and it's trying to compile the inputs. The next, what you see is starting up one processes. That is actually the Java process running in the background. And it is finalized with 2 lines below, simulation completed, took 1 millisecond, 1000 milliseconds, so 1 second basically, which is really, really slow today, probably due to my screen share. And the comment again from the file that says your results can be found in the folder you specified. And in this case, we were in the AMIRIS folder, and it will be in here. And it will be named after the scenario, after the file that we entered. So it was scenario YAML. And therefore, it creates a folder scenario and puts all of the outputs in here. Okay. So there is the outputs of the simulation. Okay. So outputs in here, scenario. I mean, we typically call our files scenarios. So scenario is not really a smart thing to name a folder. So what we now do is we run again, but we redirect our output. So basically what we do is we add an additional command, -o, which you can find if you press AMIRIS run -h, you will get the help and will show you all the command options that are there. And here you can see that there is a -o output where we can specify the directory to save the file to, the results to. And we will simply do -o, and then because we are using the simple scenario, we will add simple and it will run again. Create a simple folder where we find the scenario file again. So we moved it. Okay, I will just delete the scenario because it's not used. Okay, so it's as simple as that. Pun intended. And now you've moved the output file and ordered it. If we look at the results folder now, in here, simple scenario, we find the outputs of each of the agents that were in this simulation, that were included in the simulation. And we can open any of these files. For example, we can open the, I don't know what I'm opening here, obviously energy exchange file here, right? So I will just open the energy exchange file here for you. And this energy exchange file is, or any of these result files, is structured in a specific way. So firstly, in the first column, you will always find the agent ID. Yeah, as here, same file, only in Excel. I will just go over there. So the first column will always show the agent ID. Each agent has a unique ID, so you will always know from which part of the simulation this output came from. And you will also know from the time step at which time this output was generated. And all further columns indicate output columns that you can specify. So for example, our agent number 1, the agent energy exchange, outputted at the first simulation hour, which is just the year January 1st, first hour of January 1st, 2021. We find that it awarded a total power of 12 gigawatts, around about 12 gigawatts, for a price of 267 euros per megawatt hour. Okay, sounds a bit strange, That is, it is really just a dummy simulation. It's only for proving it's working. You can just see how it works in general. It's not a complicated real world configured, parameterized anything. It's just for showcasing that AMIRIS is running. We will have a more detailed and more valuable use case in the next minutes. Okay. Any questions up until here? Anyone succeed? Did anyone succeed? Yes. 1++, that's great. 2. Cool. Does anyone have trouble? Maybe the more important question. Does anyone have trouble? Anyone need more time? Please indicate. No. Okay. So, yeah. Now, you've run the simulation of AMIRIS, but actually what is in this simulation? How to parameterize AMIRIS? That is the next big part. I try to explain every, or not every, the most important parts of AMIRIS and how it's parameterized to you. So if there are any questions, do not hesitate to interrupt me. If there is anything unclear, if I miss anything important or stuff like that, just interrupt me, okay? Okay. So if you open, now I mentioned before that the scenario file is an important file and it defines what the simulation is actually doing. So we're going back to the examples folder, and in the examples folder, go to Germany 2019 and open up this scenario YAML in your favorite text editor. And you will see that there are in general 5 sections, 4 or 5 sections. If you highlight these, this is schema, general properties, variables, agents, and contracts. Okay, so these are all information required by AMIRIS, and these fulfill different parts. So the schema is the definition of what a valid agent, what agents exist in the simulation, what can be there, what in principle you could put into the simulation, so what AMIRIS knows and understands, and what kind of contracts they can provide, so how they interact with each other. That is the schema. It's basically a lookup table used for validation. The general properties defines when a simulation starts and ends. It's a very short chapter of the schema file, but important because you need to know when the simulation should start and end. The variable section is an optional section. It's only there for YAML anchors to make it configurations more convenient for you. If you do not know what that is, we will come to that later. The agent section, which is probably the most important one, which states what agents are in the simulation and how they are parameterized. And last but not least, the contract section, which defines how these agents interact. Okay, so as I mentioned, the file is usually called scenario YAML, but it's just a convention from us, and you can name it anything you like. And we will also rename it later, so that is not an issue. And important is that you can split the scenario YAML into separate files to make it more easily handleable. For example, the schema is part of the scenario YAML, but in general, it's not changed. So you can extract the schema from one file and reuse it in many others. And you do not need to copy and paste it over in the files over and over again. In order to use that, we defined a special command which is not part of the YAML syntax, but FAME does this. And FAME understands this include command, and it allows you to actually use a schema file that is provided elsewhere. So this is a relative or absolute reference to a schema file that you can put in here, and it will help you to find to keep this file shorter. And is also used for the contracts, because contracts are split in individual files that each control a certain element of the simulation. So we will see it also later that this makes things a little easier to handle. Okay, so again, that was the more abstract overview. Let's get a little bit into the details. So if you look along in your scenario YAML, and did you detect the general properties section right at the top, actually? So here the general properties. You can ignore the output section by now and only have a look at the simulation part. And this is important. These three numbers determine your simulation, basically. They determine when your simulation starts, when your simulation stops, and what kind of random seed is used for random processes within your simulation, if there are any random processes in your simulation. They are usually not in the standard configuration of AMIRIS. And it is important to note that these timestamps over there, they look a little bit odd. We'll see that there is an underscore in there. These are not to confuse with UTC timestamps. They are simulation timestamps. So they refer to the simulation time. And in our world, the simulation time means that we are always having 365 days per year. So every year has 8,760 hours. There is a certain, yeah, I mean, it breaks with reality, but there's an idea behind it that we can simply use 1 year of configuration and apply it to another year, and not like, I don't know, make up extra dates for if there is a leap year or stuff like that. So yeah, so the idea here is to have more transferable data and use this for scenario parameterization for the future, and for example, use any weather year for any other simulation, for example. Okay. And if you maybe recognized, we're using the YAML format, so yet another markup language. YAML is short for, and YAML is indentation based, and we always need to use 2 spaces. So if you're using tabs and stuff like that, this will fail and break horribly, and it will be a very long, very strange error message. So friendly hint from my side, YAML, if you're not familiar with it, always use spaces, and it saves you a lot of trouble. Okay. Now, the next part, important part, agents. Agents, you can see also in the file, or just open it again. So if you open the agents, it's a rather long section here, and it is a list indicated by this dash over here. Each of these dashes is a list item, indicates a list item. And these agents, section agents, contains a list of individual agents. In this example here, we have 3 agents. There are more in the actual file, and they are like the borders of these agents are indicated by the yellow borders here. So each agent requires a type. What kind of agent is it? What does it do? What can it do, actually? A unique ID within the simulation. So this ID is unique because that's how agents actually talk with each other. And attributes, which is simply another name for input parameters. For these attributes, each attribute can have a name and a value, and the values can be of type integer, floating points, enums, or even time series. These and as you can see here, for example, there can be also complex. There can be also complex values. Time series, by the way, so can also be replaced by a single value. So in the example below here, you see that price for the fuels is actually a time series, but it can also always be replaced by a simple single value. So to make it easier, so you don't need to create a file which only contains one value, you can simply put in the value in there. It will also work. Yeah, and you can see here that we support complex structures of inputs. So you can have, for example, an attribute called fuel prices, which is itself a list containing, again, another block of different items itself, which have a different structure. So you can go very deep into that and define if you require it from the simulation point. You can define complex inputs. Yeah, not that I would recommend it, but it's possible. And the structure of these attributes, they're dependent on the type of the agents. So you will see we have 3 different types of agents. We have fuels markets, a carbon market, and an energy exchange. And these have different attributes and different types of attributes and different structures of attributes. That is because these different agents need different inputs. And what kind of agents and what kind of attributes they require is defined in the schema file, which we will have a look at in a second. Okay, I already mentioned every agent needs a unique ID within the simulation. FAME will make sure of that. If you use an NID twice, you will get an error message. Okay. I mentioned time series can be an input. Time series are basically comma-separated value files, so CSV files, that allow you to provide time-dependent inputs. And there's only like 2 columns. The first one is the timestamp column, and the second one is the value column. So within the configuration file, let's have a look in here. Within the configuration file, you're pointing to a file, time series, CO2 prices, for example. Let's just jump in, time series, and CO2 prices. And this defines this time-dependent value for this time series, for example. Yeah, it's exactly the same. And it's a two column format, so timestamp and value, as I mentioned. And the timestamps also take this special format with this underscore here to just make it clear this is, again, not a UTC time, but just a simulation time. Yeah, there is a link in the chat that explains how these two differ exactly. But I mean, they are largely in parallel, but there's only one like minor easy error that is made because in a leap year, we cut off the last day. So there is no 31st of December in a leap year, and that might actually lead to a strange behavior if you're not aware of that. But that's basically it. Okay. Yeah, and the idea was to apply these time series across simulations and for different years. And you will recognize here that this timestamp, it does not start at the beginning of the simulation. The simulation starts at January 1st, but this timestamp goes to January 7th. So you are missing a lot of data in here, actually. So there is not for every hour, not even for every day, you have values for the CO2 price. And that is not an issue because AMIRIS will interpolate the values it finds here. You need to look up in the code actually how it interpolates. So if it's like a stepwise function or if it smoothly interpolates, but usually it's according with the data availability. So yeah. Okay, 2 remarks. Additional columns, also empty ones, are not allowed. So if you encounter additional semicolons, you better remove them, otherwise it might break. And also you cannot have like incomplete lines where a timestamp or a value is missing. So you also need to remove these incomplete lines because this will also break. These are just safeguards that you're working with the proper files and not having like an incomplete file. Okay. Other questions so far? Or no? Okay. So now I mentioned that before the agents interact with each other via sending data to each other. But how actually is this done? Because in AMIRIS, this can be parameterized as well. It's not hard coded in the simulation, but it can be parameterized as well. So and this is done via so-called contracts. Contracts kind of are definitions that say, when does an agent send what data to which other agent? That's all. And so let's have this example. In this example, we have an energy exchange with the agent ID 1 and a trader with an agent ID of 2. And our trader wants to send a bit to the energy exchange. And in this case, it defines a contract stating, I, the sender ID 2, want to send to the receiver ID 1, the energy exchange, bits, the product, starting at the delivery time of 0, which is in our case the beginning of the simulation, and do this every hour. So every 3,600 steps or seconds, I will want to repeat that. And this will make our agent actually do that and send the bits. By this defines the action happening in the simulation. And the energy exchange in turn will have a contract stating, I, the energy exchange ID 1, will send to you, trader ID 2, the awards from my market clearing action. After you've sent it to me, you send it to me at 0, I will return it, time of 1, and I will also do this every hour. So this is also a contract happening in here. And these two contracts you can find in the contracts folder. We will just look at here. But one important note, you can define agents without contracts. So if you put agents in the in your agent list, but do not add them any contracts, there is no check, and these agents, they will be there in the simulation, but they will simply do nothing. So just a warning in here, it's not sufficient to put the agent within the in the simulation. You need also to assign contracts to it in order for this agent to actually act. Okay. So let's have a look at the contracts part. Almost finished with theory. So let's go into the contracts folder. So in Germany 2019, you find the contracts folder, and these contracts are all included by in the scenario file automatically. And if you open this conventional YAML, you will find that there are contracts in here that define these interactions between the agents. So what we find is that there are many interactions between the agents, and that very often contracts are quite similar. So what we do is we have a short notation available that allows us to perform one action multiple times. So one sender can can send to multiple receivers. Multiple receivers can send to one. Multiple senders can send to one receiver, and multiple senders can send to also to multiple receivers at the same time. But this is done not each to everyone, but only each to every other one. So does that make sense? To one of the receivers. So in the example case you see here to the right, here we have two senders, 2 and 5, which will both be active and both have the same contract, and both will send to the receiver 1. In the other case, one sender sends the same contract to 2 different receivers. And on the bottom one, you see that each sender sends to one receiver. So 1 sends to 11, 2 sends to 12, and 3 sends to 13. So it's a one-to-one in the M2M one. Okay, and even then, it's still tedious to parameterize. Therefore, we use because sender and receiver lists often repeat. So in order to make this more easy, we include YAML anchors, and anchors are simply shortcut notations that are defined as an anchor with an AND notation, with a name and something that is to be kind of referenced, and the actual reference to that will be replaced. So to make it clear in our actual example file for the conventionals in here, the first entry in here simply means sender ID will be the builders, so all of the builders, and builders refers to this list of agents. These list of agents will send to all of the receivers, which will be the operators, which is the other list in here. So this line actually stands for 2000 will send to 500, 2001 to 501, 2002 to 502, and so on to 2005 to 505. So this replaces 5 individual contracts, and the builders are, or for example, the operators are used quite often. So if you have an additional operator agent, you simply need to add it on the top here without changing the contracts down below. Okay. Last thing, I mentioned it, schema. Let's go over it very quickly. If you look at the schema file, just so you know what it's about, the schema file resides also in the scenario folder, and the schema file is simply a validation structure that defines what types of agents exist, for example, an energy exchange agent, what products they can provide, for example, awards, what kind of attributes they require, in our case, a distribution method and a gate closure info, how these attributes, what type of attributes they are. So distribution method is an enum and gate closure is an integer. And if these attributes are mandatory or optional, if they are lists, yes or no, and if there are some value restrictions that apply. So for example, the distribution method is an enum and it can only take the values same shares or randomize in this example. Okay. And these values are then used to validate the actual scenario YAML. So this is the part from the scenario YAML. There you see type energy exchange, and it refers to this energy exchange type. And this attribute distribution method refers to this attribute type distribution method with a value same shares that is a kind of enum and contained in the values section here. So this makes sure that you cannot do any typos or anything, any other errors, because it will be validated. If you make any error, you will get an hopefully meaningful error message. Okay, you can use this file to look up what options you actually have for parameterization and what is to be considered. But it's way easier, to be honest, to look at our wiki pages for AMIRIS, where for each agent and each agent type, you will get a very detailed explanation of what inputs they have, what interactions they do, what kind of methods they apply, and stuff like that. Okay, and last warning, do not change this file. It's based on Java code. So basically, if you change this file, you will likely end up with a not working simulation because it refers to Java code and is kind of its equivalent for the Python validation tool. Okay.
Christoph, in the meantime, we got a question in the chat about visualization of the market structure. And yeah, the question is, it's probably very easy to lose track about all the agents, and I think I can also answer it because we're working on a graphical user interface which represents then the market structure of the files Christoph presented to you. So basically the scenario YAML is implemented there, and it's in a beta phase, so probably published soon. And then you can also use a graphical user interface and spend less time working in your text editor, hopefully.
That's true. Thank you, Felix, for interrupting. And good question, Lukas. Okay. Yeah, I've really brought you enough. Let's use the time for actually doing something. So let's run the Germany scenario. So let's simply do AMIRIS run -J for the AMIRIS executable, -S for example Germany scenario YAML, and -O, let's say Germany, to make a new folder where this is gathered into. Okay. Well, I think it's quite self-explanatory. Simply change the -S and the -O part, and you will start running AMIRIS. So now the config file has been compiled completely. It has been handed over to FAME core to execute the simulation in Java. The simulation has started up. That is indicated by the starting up message. And it will take, usually, if I'm not screen sharing, it will take about 20, 25 maybe seconds or so. Probably takes a little longer today. Indicate in the chat if it completes, if your simulation completed before mine. It should be on anything like, I don't know, except maybe a handheld PC. Something should work faster today. Oh my. Oh, okay, 3 times. Okay. Okay, now the simulation has completed, and now comes the extraction part. So you see that a new folder, Germany, has been created, and in it the scenario folder. And now the files are extracted. This is done one by one, but we need to have a look at the energy exchange. For example, it has already been completely extracted, so I can simply open it right now, although the extraction process is still running. Okay. And what you see in this energy exchange CSV file, as mentioned before, you see the agent ID, which is 1. You see the time steps neatly aligned. It's already sorted already. And you will see the, for example, electricity price in Germany kind of fitted to a historical time of 2019. And if you plot this in a graph, you will see this structure of electricity prices. Yeah. And this actually quite good resembles the actual historical price time series. If you want to check it, you're welcome to do so. Yeah. So here you see the prices in euros per megawatt hour and 8,700 steps. So over 1 year, the price time series for Germany in 2019 as calculated by AMIRIS. Okay. Maybe I'm saving this just for. Maybe I'm not saving this. I don't know. Okay. Did anyone succeed? Plus plus in the chat, please. Plus plus, plus plus. Very nice. Okay. Faster than me, obviously. Okay, now let's change something. So you've seen the results. Let's simply change something. For example, let's change and go to a high gas price or something, right? So what we do now is we go again into the Germany. No, that's wrong. Into the examples, Germany folder, and just copy the scenario file. I will just copy it and rename it to scenario high gas price. I open this scenario file, and now we're doing some changes. So I'm searching for the fuels market in here, which is quite on the top, agent number 4, line 37, and go to the fuel price natural gas. For example, here we have fuel type natural gas, and what was formerly, I don't know, natural gas cost of maybe 15 or 20 euros per megawatt hour, I will simply replace by 150, which is quite expensive, but well, now we're used to almost anything. And this scenario I will run using the same command as before. So I simply change here the scenario YAML. Scenario high gas price YAML, and put it in the same folder. It will create a different subfolder because it's named after the scenario file. So we keep the -O for Germany and hit enter. Okay, takes another 80 seconds for me, probably. Indicate with plus plus if you're faster than me. Oh, god damn it, you have a high-end computer. Okay. If you're ready, you know what to do. So basically, just go back into the Germany folder, where we should have now a new folder called scenario high gas price with results in. And from these results, you can open up the energy exchange again and see how the price structure has changed. Remember if you have the other scenario, the other energy exchange file still open. Excel will complain if you're using Microsoft Excel, and you need to rename one of the files. Okay, Zane and Tars, both done. Cool. Still waiting. Ah, here we go. And energy has already decompressed, so we can have a look at the energy exchange. Here we go. Tack, tack. And having a look at the electricity prices, we see that electricity prices take a slightly different structure with now super high peak prices of up to 350 euros per megawatt hour. And yeah, winter times are tough now, price-wise. Cool. So one last experiment. This is still running. So now let's add a new trader. No, let's go to examples, Germany. And let's go back to the original file, copy it, and add more PV. Let's say more PV in this case. And now we add a new agent just for fun. So you better scroll down quite a bit, not too much to the bottom, but you might find an agent called variable renewable operator. It's called the agent 10 at line 315. So what we're doing now, we are copying it. We're copying this agent. And we need to assign a new unique agent ID. So let's see. If we check for 11, for example, we can try it. But if we see ID 11, oh, there is already the renewable trader. Okay, that's not good. Let's check another one. Maybe, I don't know, 19. 19 is available. Okay, so let's use ID number 19. And so we now created a variable renewable operator number 19, or ID 19, and we assign it, let's say, why not, 100 additional gigawatts. Okay, 103 zeros, yes. So we now, with the same solar profile, we added in, let's say, a way lot of rooftop PV, for example. So all of Germany has been now, maybe not all of Germany, but a lot of Germany has now additional rooftop PV, and we have 100 gigawatts additional PV power. But as I mentioned earlier, if you do not assign contracts for this agent won't do anything. So if you would rerun it now, you would not see any difference. So what you need to do now is you need to also add this agent to the contracted agents. And for this, I'll simply copy the contracts folder and rename the copy to contracts PV, or contracts more PV, let's say, because I need to modify them. And instead of, and in the very last line, you see that we include the contracts, but now we need to include the new one, the new folder. So I change this to include contracts with more PV. Okay, so far so good. But I still need to assign the agent. So I go to contracts more PV and open the renewables system operator YAML. And in here, I find the agent that I originally copied from, number 10. And I simply need to add in number 19 on the list of renewables here. And that will replace or insert our new agent number 19 at all places where it is required. So simply add number 19 in the add renewables list in here, save the contract, and you're good to go. Okay, let's do it again. Compile the scenario. Scenario, more PV YAML. Here you go. Was that too fast or did it work? Did you follow? Was quick but managed. Worked. Cool. That's nice. That's nice. Yeah. There you go. So again, it takes a long time and we only have a few more seconds on my machine. So I will skip the waiting for the results part. So if you go back to the AMIRIS folder, in the Germany folder, you will find a new folder called Scenario More PV. And if you open up the energy exchange again, you will find that now prices are depressingly low in the summertime when PV strikes and produces a lot of feed in. Okay, So due to the short time, I will just skip ahead with the actual results showing to you. If you really want to know it, you need to try for yourself. And let's give a few final remarks from our side. So we try to follow with the FAIR for Research software principles. In the presentation, you find a lot of links where we try to make AMIRIS findable, accessible, interoperable, and also reusable from the software perspective. And you're free to check these links. We will upload the presentation to Zenodo also, so you can also easily access this from our Zenodo group, our AMIRIS Zenodo group. And yeah, if you got application ideas, or we have some application ideas maybe that you could use. So if you want to use AMIRIS, you could apply it to your market zone if you're not based in Germany, or you can use it for different years. You can look at effects of different weather years or policy schemes or fuel prices on your system, and for example, assess not only market prices, but also system costs or the refinancing situation of different types of agents, for example. And actually, we're doing this in TradeRes, which is a European project that will present it tomorrow and also in one of the keynotes. But I will also show the comparison of support schemes for renewables for a German case study from the TradeRes project, and that is also an AMIRIS application. So if you're interested in how this applies, you're welcome to see that talk tomorrow. And yeah, feel free to use AMIRIS. Ask us questions in the OpenMod forum. We have an OpenMod forum link also. Publish your scenarios, cite us at our JOS publication, report difficulties, report issues, post your ideas of how we should improve it, make features requests and stuff like that. And also, if you're very welcome to improve AMIRIS, modify agents or so, and make pull requests to our repository, of course. And if you got anything to talk to us, if you want to join forces with us, discuss modeling ideas or anything like that, get in contact and use AMIRIS at DLR or visit our website that we also have linked in the model workshop description. And last, we would ask you for your opinion and your rating of this workshop, if it helped you in any case, if you you had got any insights from it. So please enter your rating for this workshop at Slido, and give us any comments in the chat or at Slido how we could improve or what would help you. Yeah, thank you.
Thank you very much, Christoph. Right on time. Super interesting. Yeah, round of applause. Thank you, Def. You'll find also the recording online after.